All right, and the last question then for the day is why isn't my chiral molecule separating? It's again not exactly a straightforward question to answer, and there's a couple of scenarios that could be at play. First, it could very well be that you're using the wrong column, or it could be a poor method. It's possible that there could be some instrument issue that's taking place, so it's not actually related to the column itself, either an issue with the detector, say, or an issue with the pump not metering the correct solvent. Poor interaction with the column, or too many interactions with the column, or blocked interactions with the column itself. I have an example of what that will look like, but it just is possible that the analyte that you're using does not interact very well with the column that you're trying to use. So when I say wrong column or poor method, specifically wrong column, usually we'll ask what kind of method development has been performed. A lot of people are perhaps under the false assumption that one column can separate all your compounds. And there's a reason why we have 24 different chiral stationary phases. The reality is, as I pointed out in the separations mechanism, you can't predict what column is going to work. And even if you make tweaks to your molecules, if it's in the same class of molecules, there could be a completely different column that works better for that analyte. So I say here, Chiral Pack IJ is a great column, but it doesn't separate everything. So what kind of method development has been performed? Do you know for sure that the column that you're using actually separates the molecule, or are you just guessing? If you're just guessing, it could be you just need to try a different column. Or if it has stopped working, as I pointed out in the previous section, there could be some other issues that are going on, either clogged inlet frit or something like that. It could be that it's a poor method. Has the method robustness been assessed? And by this, I'm talking about operating in a plane of stability and not on an edge of instability. If you have a separation that's extremely sensitive to the percentage of alcohol, for instance, and you have an issue with the pump, where maybe rather than pumping 5% alcohol, it's pumping 10% alcohol, that could be enough to cause a loss of separation, which could be picked up if you were doing a robustness study. And again, might not be that it's an issue with the column, it might be an issue somewhere else that we need to address. Maybe you're using the wrong additive. Acidic molecules, as I pointed out in the previous section, require acidic additives like TFA or acetic acid. Basic molecules need basic additives like TEA or DEA, but just because TFA, for instance, is our go-to for acidic molecules doesn't mean that it's always going to give you the best peak shape. There might need to be some optimization that can take place there, which I do have an example of what that looks like. It might be that it's just the wrong additive that you're using. So we talked about method robustness testing. I won't go into it too much because my colleague Bill Champion did a webinar a few months ago on this topic, but when you have, say you've done your method development screening and you find a nice separation, the next step would be to check the method robustness and try to figure out what parameters from that screening are actually controlling the chiral separation. We want to have a sense, for instance, of what kind of variability exists within changing temperature, what kind of variability exists within changing the composition of the mobile phase, because it can help us determine whether or not this is a very sensitive chiral separation that we need to be cognizant of when we're taking it forward into our further optimization. So this is what we would call central composite design, where we pick these points that are out on the corners, and we can kind of see the extremes of how the chromatography reacts. This is in juxtaposition to what we would call a random walk, where yes, technically in this case, we are checking different mobile phase compositions, we are checking different temperatures, but there really isn't anything that's linking them to each other. So if we go from D prime to E, for instance, and we see a pretty dramatic change in the separation, we don't know, is it the temperature that's doing it, because we have a pretty large temperature swing, or is it the difference in mobile phase composition? So the central composite design is helpful in this endeavor. This is a separation of 4 cannabinoids to kind of demonstrate this for you. This was this first here. This is temperature dependency check. So I held the mobile phase constant, 95.5 hexane ethanol, and I went from 35 degrees all the way down to 15 degrees. And you can see for the most part, other than slightly longer retention at the lower temperatures, which is expected, there isn't a dramatic change overall in the selectivity. There isn't really too much of a change overall. Certainly there isn't in dilution order or anything else related to the performance of the chromatography. However, if I go and I went and tried to assess the dependency of the mobile phase, I kept it temperature consistent at 30 degrees, and I went from my initial starting conditions, 95.5, up to 99.1. You can see if we're operating within the 3 to 5% range for ethanol, that the chromatography does start to decrease slightly, but there's still good baseline resolution. When I go to 98.2 and then 99.1, the chromatography is almost undistinguishable from what it was previously. And this would be important to know, especially if you were to choose these conditions here at 97.3 to operate this analysis at. I mentioned if you had some pump issue where all of a sudden you weren't metering out the correct amount of alcohol, very quickly you could go from a nice baseline separation of all 4 of these cannabinoids to nothing. And you might think that perhaps it's a column issue, when really it could be an instrument issue. But you would know that you needed to be careful if you had done that robustness testing to see that when you made this jump, there was a pretty dramatic change. I mentioned wrong additives. In this case here, this is no additive versus additive. Here, this separation, this is a basic molecule, chlorphenyramine, has both the pyridine and this tertiary amine moiety stuck to it. If you were to try to do the separation on ADH with hexane IPA 90-10 conditions with no base, you'd see one large peak that tails quite substantially. But just adding in 0.1% DEA to the mobile phase gives you 2 nice sharp peaks. So not having an additive in this case would perhaps give you the false impression that AD is not the right column for this separation, when in fact it is. It's just you needed base in the mobile phase. This was an interesting case where generally we don't think of alcohols as being additives, quote unquote, in the separation. But if you had this was a separation on IG, mobile phase, hexane, DCM, DEA. So you had DEA in the mobile phase already. It was a basic molecule. Under the screening conditions here, IG showed one broad peak, and we did some other optimization on the side for other reasons, but we ended up redoing the screening with 2% ethanol in the mobile phase. And just by adding 2% ethanol to the mobile phase, we went from, again, one large broad peak to 2 nice peaks. So there's obviously something going on the column where ethanol is helping with the separation. It could be going back to those interactions that we talked about before, either some change in solvation status. It could be the molecule fits better or interacts differently with the chiral stationary phase now. But alcohols can also play a kind of an important role in being able to elicit a good chiral separation. I mentioned the pumping issues before and instrument issues. I'll go back to this example again just to reiterate that, where these were pre-mixed mobile phases, so I know for sure that the ratios were exact. But if you were running your instrument and say you had it set for 97.3 and you had it set up so that it was metering itself, it was pumping 97% and 3%, and all of a sudden you started seeing these results over here, it might, again, not be the column, it might be an issue with the pump, or it might be an instrument issue somewhere else. So things to be aware of, to be on the lookout for. Method development challenges, I mentioned too many interactions or not enough interactions, or interactions that exist but are just blocked by the sheer size of the molecule. So this is a method development challenge example here. where we have too many interactions. We have stereocenters that are buried within the molecule itself, and it's also unclear what additive we should probably be using because we have both acidic and basic functionality. So I'll just show you first the screening result. There was only one column that showed any sort of separation. It was OZ3R. It was a reverse phase screening that we did. Method is shown here. Initially, we just did it normal or under neutral conditions, so acetonitrile water. If we zoom in, we can see here we have what looks to be a partial separation of two peaks and then some coelution going on here. This molecule is, it's got 4 isomers, it's got 2 stereocenters, and this is what it looks like. It's a very large polypeptide. I don't remember the specific locations of the amino acid variants, but one of them was towards the end of the molecule here, and the other one was kind of buried within the center of the molecule here. So it would not be unreasonable to assume that the interaction that's kind of out at the end of this long polypeptide chain could be these 2 peaks here. So it's able to interact and get within those pockets, those chiral grooves that I showed before. Whereas there's coelution here of the interaction or the amino acid variant that's buried within this chain here. There's just simply too much other stuff going on to allow for that moiety to fit within that chiral groove, and so it's not going to show any sort of chiral separation. Generally, in this particular case, polypeptides do better with acidic additives, but you can play around with it. You might need to use TFA. You might need to increase TFA from 0.1% to 0.2%. You might need a mixture of additives. You can do both acid and basic additives. You can use a cheotropic salt, which is what we did in this particular case. Potassium hexafluorophosphate does a really good job with especially amino acid variants like this, keeping the polypeptide in more of a linear conformation instead of its natural inclination to want to curl up on itself and potentially bury those interactions even more so than they are. And you might need to look at coupling columns or going back to that central composite design to figure out what sort of method parameters have an effect on the separation, to figure out maybe I need to change temperature, maybe I need to change additive, whatever the case may be. So at this point, I believe I've answered all 3 of those questions kind of in full. I will just highlight some new information for you, some things that you might not be aware of, some new columns that we have. Our newest column I mentioned in the intro was Chiral Pack IJ. It's the immobilized version of chiral cell OJ. And like you would expect with an immobilized column, the access to extended range solvents dramatically improves its separations capability. So this is a separation here of warfarin on OJH and IJ normal phase conditions. It separates, but the peak shape is poor. Going to extended range conditions here with THF, you see there's a dramatic improvement in the peak shape and a much nicer looking chromatography. So it's, as I mentioned, the immobilized version of IJ, very similar separations as you can see here between IJ and OJ. So if you have a separation on OJ and you're looking to migrate it over to IJ, there's a very good chance that it will move over without any sort of an issue. It's currently available in 3 and 5 micron, so analytical particle sizes, but 10 and 20 micron are coming soon if that's something that you are interested in. I have an email address at the end of this presentation here that you can send that question to, and we'll be happy to keep you informed for when those are coming. Again, just improved separations here, going from normal phase conditions to extended range conditions. This example here, 5-methyl-5-phenylhadentane, and then diisopyramide normal phase conditions for OJH here, hexane ethanol. Not quite baseline resolved, but going to extended range conditions with THF, a nice baseline resolution. And again here, under normal phase conditions in red and blue, going to extended range conditions here in green, nice baseline resolution on IJ. One last thing, our website, a lot of very good information up on our website. I'll point out one thing in particular at the moment here, which is our instruction manuals. If you go to the main page, click on instruction manuals, we have all of them up on our website. I would highly encourage you to read those before you use the columns, especially in helping to answer this question, why is my column not working? The instruction manuals list all of the column limitations and give you some method development suggestions as well to help you avoid any sorts of potential pitfalls or issues that you might have with a particular column. We're currently working on updating all of these instruction manuals, especially with the launch of IJ. So please check those out, even if you have a copy currently. There's some new information that's located in those instruction manuals that you might find helpful. And then the email address, as I mentioned, if you have general column chromatography questions or questions about method development, please feel free to email us at questions@cti.daicel.com. If you have a question about this presentation specifically, or chromatography or column questions, you can please feel free to email me as well. I do monitor the questions email address as well. So if you're looking to avoid me answering it, unfortunately, you'll have to go to Kristen Ferrante, kferrante at cti.daicel.com to bypass me. No, just kidding. And then we do have other previous webinars as well: chiral method development, sub 2 micron method robustness, column validation, and so forth. So if you're interested in those, please feel free again to email either myself or Kristen. She can send you the links for all of those. Again, that was kferrante at cti.daicel.com. That's it for me. I'm going to go ahead and pass it back over to Kristen for some closing remarks.
That was great, Wes. Thank you so much, and thank you for all of you for attending. We hope you've enjoyed today's webinar. Please contact us with any questions and stay tuned for our future presentations. Have a great day, everyone.